All right, welcome back. This is part 2 of working with a single trial for force platform analyses, kind of from a sports science perspective. So in the previous video, we imported the trial and left off here where we filtered the vertical force data. Our objective here is to start processing that data. So the order at which this happens can be somewhat customized based on your purposes, but I'll always start with calculating some basic characteristics of the kind of jumper or the athlete here in this case, depending on your movement trial. So since the data we're working with are a counter movement vertical jump, we'll start with calculating a body weight. So I'll call this a W. And what we're going to do is if I were to recall this, plot, there's been plenty of videos and discussion on this by Dr. Jason Lake and the Hawk and Dynamics team about having enough samples here to calculate a body weight value and other things. So here you can see we do have what looks to be enough for 1,000, but it's kind of touchy for this trial. So what we're going to use is a different value. We're going to use 500, but remember that can be a crucial methodological decision. So make sure you're aware of the value that you're choosing and why you're choosing it. So we're going to use, remember we have from the first video, 1,000 hertz sampling rate. So 1,000 here on the number of data points means 1 second. So we're going to use 500 here for a half second. All right, so just something to make sure we're aware of. And so what we're going to do is calculate the average of that vertical force during the first half second of the trial. So we're going to do mean, that's MATLAB's function to calculate the average. It will be the mean of FZ, and we'll open a new parenthesis here to specify where we want to calculate the average. If I just left it like this, it would calculate the mean of the entire column, all 6,000 data points. But I only want to do the first 500. Okay. Here, if you had a longer trial, ideally you would do 1,000. We're just going to do 500 for this purpose. Now I'm going to close that parenthesis, and then again close the parenthesis for the mean. Okay, and this will be body weight in units of newtons. And so if I run this and go to my command window, you'll see there's the body weight. So we've got actually large body weight here, a large athlete. If I were to look at that weight, oops. Now one thing you hate if you're like me is it gives it scientific notation. You could spend your time trying to read that, but if in your command window you want all the numbers to display a certain way, for instance me, I like it to be 2 decimal places, small type format, space, bank, and then when I do that again, it will round my values to 2 decimal places like they would in a bank, right? $1, or pound or euro or wherever your currency is. So that's what we'll like to do there. Now another thing we'll like to do is, if you're familiar with the work of Dr. Jason Lake and how to calculate the start of a jump, and some of his other colleagues use this method as well. So what we're going to do is stick kind of with that because it seems to be one of the more popular ways to do it. So we'll also need a maximum force value during this time period where we calculated body weight. So what I'll do is call this W max for weight max. And this is going to use a MATLAB function called max. Obviously, it's going to pull the maximum value of the FZ during that same half-second time period. So the only thing that changed here was instead of using mean, we're using max. Okay, and if I suppress this and add my note, this is the maximum FZ during the weight calculation period. All right, now that's going to be important for certain determination methods for what values to use to determine the start of the movement. And if I do this line without suppressing, you'll see what that max value was. If I compare that to body weight, you'll see that value is a little different. So in the time period where we calculated body weight, here's the body weight value, but here's the maximum value during that period. Okay. Now moving on with that start method, we're going to use the plus or minus 5 standard deviation method to calculate the initiation of the counter movement jump. Personally, I've used other methods in the past, but it does seem like this may be the more ideal way to go about it, is using 5 standard deviations and plus or minus threshold. So we're going to stick with that here. So I'm going to create a variable called SD5. That's going to be my 5 standard deviations. We're going to use MATLAB's function called std, that is standard deviation. We're going to do of the FZ during that half-second wait period. Okay, but now I'm going to multiply that by 5. Okay, just asterisk is multiplication sign, and we're going to do 5. And we suppress that, and this is 5 standard deviations during the wait calculation period. And again, you don't have to put the notes in the green text after the percent sign like I do, but just keeps everything organized for if you have a script and you don't look at it for a long time and then you come back to it and you go, wow, what was I doing? All right, the next bit is to calculate mass. I'll name this M. Basic mechanics would say if we take the body weight and divide by gravitational acceleration, the absolute value of gravitational acceleration, we'll get body mass in units of kilograms. So we will specify that and give a note. And you'll see if we put that in here without suppressing this with a semicolon, you'll see the body mass of this athlete. This was a large athlete, 138 kilograms of body mass. Okay, so there's our basic parameters, things we will use to, at some point or another, detect the start of the movement. So now what we're going to do is kind of put a note here for the section. There's a step here where we need to determine, because we saw here for previously that the maximum value during the weight calculation period was actually larger than the mean. That can impact detection of the start. So what we're going to do is use some logical statements here in MATLAB, kind of saying if something meets a certain criteria, well then I want you to do this. But otherwise, if that criteria is not met, we're going to do something else. And so that's what we're doing here. Specifically, we're going to control for whether the max FZ during weight calculation is greater than the actual weight. Okay. So we'll start with an if. We're giving it the criterion that we're trying to judge against. And we're going to say if weight max is greater than or equal to body weight, we're going to detect the start of the counter movement jump using a greater than 5 standard deviation threshold. Okay, so I'm going to call this CMJ start 1, and hopefully we'll see why later. Because when we use the plus or minus, first we're going to look for whether or not there was an increase in force above the threshold. If that was not met, we'll look for a decrease. Okay, kind of like, do you increase force before you start the jump versus do you just reduce force? So I'm going to call this CMJ start 1. And so if that weight max is greater than or equal to body weight, CMJ start number 1 is going to be equal to, and what we're searching for is a data point. So when I go to FZ and I plot it, it's going to just plot the data points. I'm going to search what number of these data points, 0 to 6,000, does the criterion happen. Okay. So CMJ start 1, we're going to use MATLAB's find function. It's going to find the data point where something happens. We're going to search through the FZ data, and we're going to search for where that FZ was greater than weight max plus SD5, the 5 standard deviations. What we're going to do here is just give this a true. Oops, not in the single quote. We're just going to say true. Okay, and what this is doing is searching for a preloading, so I call it an application of force to initiate jumping if max FZ during weight calculation is greater than or equal to body weight. Okay, so I like to put those notes in here. Now, if this condition here is not met, we can type else, and underneath that we'll say if this condition above is not satisfied, CMJ start 1 is going to be equal to, again we'll do a search, we'll search FZ, and now we're going to say greater than body weight plus SD5, and we'll say true. Okay, so essentially, if the max force is not larger than body weight, we're going to use this here. Okay, so it just depends whether or not you're using weight max plus 5 standard deviations or body weight plus 5 standard deviations. And so what this is doing is search for a preload to initiate if max FZ during the weight calc is not greater than body weight. Okay. Now, after we have done our logical statements, so if this is met, do this. Otherwise, meaning if any other condition is met, we're going to use this one. After we do that, we can type an end. Okay, so this is going to search for an increase in force during preload. Oops. SD5, did I type it wrong? Oh, I didn't run my SD5 up here. So MATLAB's good. It'll tell you whether or not you made a boo-boo. You can see up here I didn't run. If you look here, there's no SD5 because I didn't run that here in the command window. So if I were to just go ahead and fix that and then run here, now I do have a CMJ start 1 and it's telling me at 1395. So if I were to now plot my FZ, which I can do here in the command window using plot. Right, so before we double clicked here, and then came here to plot, well, I can just type it here in the command window real quickly. And it's telling me that CMJ start is at frame number or data point number 1395. So if I come here at 1395, somewhere in this region is where that important stuff happens. Now there's a MATLAB function that I'd encourage you to Google search. It is called vline, like V, the letter V, and then line. Okay, so it's a specific function that you'll have to download and install, but it's very useful. And so what I'm going to do is go vline CMJ start 1, because in this graph it's going to put a vertical line in that graph where this happened, and you can tell that when the preload or increase in force above the body weight criteria happened is not actually occurring, where it should. So that tells me that there is no preload above that threshold to start the jump, meaning we're going to have to find an unload using the body weight using the body weight minus 5 standard deviation threshold. Okay, so I'm going to minimize that figure. And here what we're going to do is create what's called another CMJ start. So CMJ start, this one will be number 2 because we're going to identify these 2 different ways and then select the correct one later in the next line. So what I'm going to do here is create CMJ start 2. We're going to use the same type of logic here to find FZ, but we're going to change the greater than symbol. So this will be find. We're going to find when FZ is less than, and we're going to do weight minus SD5, and we're going to go true. And this is going to search for an unloading to initiate the jump. Alright, so if I copy this, you'll see that CMJ start 2 is at 1098. So now let's take our graph and put a vertical line here. Again, this vline function you'll have to get yourself, so you won't have this unless you have that function. But we're going to do cmj start 2. I'm going to go ahead and add a different color to that line. So if I were to just put a single quote and a color specifier, so if you Google MATLAB color specifications, it will tell you what you can do. So green would be G, magenta, kind of purple would be M, but we're going to stick to green. So that V line gets added to the graph, and you can see now that green one finding an unload. Okay, that's the one that we want. So our next little bit of logical operation is going to say we're going to pull, because remember this is CMJ start 1 in the red dash, this is CMJ start 2 in the green. So we obviously want to use the one that comes first between these two. Okay, so that'll be our next bit. So I'll minimize that figure. This is going to identify the real start for use in processing. Okay, and essentially we're asking it, does preload or unload happen first? Okay, so we'll use another logical operator. Here we're going to say if, and we're going to say if CMJ start 1, remember that was preload, is less than CMJ start 2. So does the data point, essentially the time, even though it's not time, it's data point frame number. If the data point number for preload is less than the data point number for unload, what we're going to do is say CMJ start. Now this has no number identifier because that's the one we're going to actually use. So we're isolating that variable, and we're going to say that's equal to CMJ start 1. So that would say start is via preload. We're going to do else, meaning otherwise. So otherwise, if anything but this right here is met, CMJ start is going to be equal to CMJ start 2. Okay. Now I will end that logical operator. I'll suppress that. All right, and so if we run this, and we'll look here and say CMJ start is given the CMJ start 2. It's matching those. Right, and if you remember when we graphed those, CMJ start 1 was red, CMJ start 2 was green, and so obviously we want CMJ 2 to be what we're going to use. So that's what we're doing. If we wanted to give this its note, start is via unload. All right, so we've identified the time at which that start occurs. Now another method that I'm just now recently starting to adopt, I was a long, stubborn holdover of integrating. So if we're thinking of the force curve, I got rid of my graph. If I bring it back, right, I always start where the person is standing still, and they stay started standing still. So I would usually have started integrations right here on that first data point, or well, calculate acceleration and then integrating. But growing in popularity method, or maybe it is popular and I'm just now finally starting to lose my stubbornness, is to do a backward search to find the most recent time or the closest time when body weight was the value of the ground reaction force. So if I were to add that V line for CMJ start back into this graph, so what we do is say that's the start. Obviously that value is not body weight. We don't want to integrate from there because we need to satisfy some necessary assumptions that the first value that we integrate will have 0 acceleration characteristics. So when we think of Newton's laws, we'll get there in a second, but we've got to meet those criteria. So that can't work here. It could work over here in the very beginning, but there's some little dips right here that if I maximize this, there's some little dips right here that could affect those integrations, and eventually we'll start to have some velocity changes and then increasing our drift as we get going on. So what we're going to do is do a quick little backward search here. Now, if we're familiar with a 2014 paper from, I believe it was Owen, I can't remember if I butchered that, sorry, but they suggested using a 30 millisecond backtrack here. I don't think necessarily that's long enough, so what I end up thinking is a 200 millisecond back search is going to be more than plenty, because for instance, at 1,000 frames per second, 30 milliseconds, right, would be 30. And so if I did a vertical line at CMJ start minus 30 and gave this kind of a magenta color, you'll see we're still here at some changes happening. So if we subtract body weight from this force value, right, so if I do FZ and we'll take it at the time of CMJ start minus 30, that's giving me this value of 1368, but if I look at body weight, it's 1356. Okay. Now, if I were to take that FZ, now this is is that if you go right here where you type in the command window and you hit the up arrow, it brings back your previous things that you ran. So I just hit the up arrow and went to 30 here. But if I change this to 200, that is a 1363 value. And if I think of what weight was again, 1356, we're getting much closer. Okay, so the acceleration and ultimately velocities we calculate are going to be much more precise in this case. Now that might just be a uniqueness to certain data sets, like the trial that I'm working with right now. So you should probably think about what would be the ideal method for you and whether or not you're going to start integrations and all those things from the very beginning, or whether or not you're going to use this kind of backward search from the start of the jump. Okay, I'm going to use 200 milliseconds and show you how that goes. So this will be a backward search to 200 milliseconds prior to the initiation. So I'm going to go create a variable called int start. It's going to be integration start, and it's going to be equal to CMJ start minus 200. So I want 200 milliseconds prior to the CMJ initiation, right? And if I were just to run this line and make sure it works, right, that would be at 898. So now if I give this a vertical line on my graph, and let's give it yellow. That's my Texas coming out of here. You'll see where it starts here, and you see that looks a little better. It's on that more flattened line. So we're going to actually start the integrations back here on that yellow line. And again, that's part of the art form of data analysis here. All right, so now what we can do is crop the force curve so that all of our math that we're going to do using Newton's law and then our mathematical integrations are going to all start from that integration start time point. So I'm going to take my FZ and I'm going to override it. Okay, so FZ equals FZ, right? New FZ is equal to old FZ. And we're going to go at int start. Remember, that's the data point when the integration start will happen. And we're going to go to the end. So we're cropping it essentially so the start, instead of being on data point number 1, it will start at data point int start, which we know is 898. So we're getting rid of those 897 data points before that integration start. So we've cropped that force curve. Now, if I were to close this figure and plot the new FZ, you'll see, there you go. That's, whoops, don't minimize. You'll see that's where the integration start will occur. Okay. What I'll do now is create a column of time data. This is going to take into account the length of the trial and knowing what the sampling frequency was that I recorded the trial at. So if we're going to create time, what we're going to do here is create an array. So an array simply is, if you look at the FZ, this is an array. It is a 5,103 row by 1 column array. And so we're going to create our own array of the same length, 5103, for time. Okay? So to create that, what we're going to do is open a parenthesis. We're going to go with a second parenthesis to do 1 divided by the sampling rate. So if you know time would be the frame number or the data point multiplied by the inverse of the sampling rate. So that's the inverse of the sampling rate right there, 1 divided by SF. Remember, the sampling rate here is 1,000. And we're going to multiply that by an array that we're going to create that starts at 0, and it goes until the length, length, that is a MATLAB function that pulls the number of data points here. So, we know it's 5103. For instance, if I just typed length FZ, it's 5103, right? So we're saying it's going to start at 0, because time will start at 0. It will go until that 5103, which is the length of FZ. But since that, starting at 0, going to this 5103 is actually going to give us 5104, because if you look here, these start at 1. But we want time to start at 0 seconds. So what I'm going to do here is subtract 1. I'll close out my parentheses. And here is time. Now if I look here, the way that that array gets created, it is 1 row by 5103 columns. We don't want that. We want it just, and most of the time this is purely aesthetic, but it can be problematic at times. We're going to switch this to be 1 column. And so just to do that, when I go back to this line, at the very end, I'll put a single quote, and that's transpose. So it's going to transpose it. Here, if I were to open time and then rerun that line with the transpose, creates it into 1 column that matches how the other data are saved. Okay, so there's time. The next bit, we're going to use Newton's second law and calculate acceleration. So I'll call this Excel. If you know this equation, it's the sum of the forces divided by mass. So the sum of the forces being Fz. We're going to subtract from Fz the weight that we calculated, and we're going to divide it by the mass that we calculated. We'll suppress that. This will be vertical acceleration. And if you want to put a note, that's the whole body center of mass. Okay, so essentially what we're doing is taking the Fz, every single one of these data points, we're subtracting body weight from it and dividing it by mass. So if I do that, we'll have acceleration that should be right at or just perfectly 0, right, to start. And if I were to plot that, we know what we're thinking about there. That acceleration should be now 0 going negatively and positively. All right, our next bit is to calculate velocity. We'll use trapezoidal cumulative integration here, so the trapezoidal method. MATLAB has an inbuilt function that makes this very easy for us. So I'll do velo, and this will be equal to cumtraps. This is MATLAB's cumulative trapezoidal integration function. And anytime you have a MATLAB function, if you want to know about it, you can just go help cumtraps. Pulls up the internet and tells you what it is. Right, so cumulative trapezoidal numerical integration might tell you how to run it. If you want to get more spicy, you can see I've got MATLAB stuff. I'm asking questions about things, but you can also do MATLAB integration and numerical integration. A bunch of different methods will pop up, and you can get the same type of information from those. Well, my Texas Wi-Fi is too slow. But there you go, and it tells you how to do it with examples. Okay, so don't be scared to Google something and put MATLAB at the end of it, because it will work. But back to the script, so we're going to calculate velocity, call it velo is equal to cumtraps. Now again, if I do not specify time, it will not be the time integral. It'll be an integral with respect to data points. So I've got to use that calculated time and the acceleration that I've calculated. Right, so it's the cumulative trapezoidal integral of acceleration with respect to time. So that will be vertical velocity of the whole body center of mass. If I paste that in there and run that, here's the velocity. Okay, and you say, yep, that looks like a vertical velocity curve. Over here, remember we stepped off the force platform to end the trial in the FZ, so it gets a little haywire towards the end. We're not going to use any of that information. So if you're familiar with that velocity curve, you say, okay, that looks like what we're working with. Now next, what we can do is also calculate an integral for position. The longer the trial you have, the more cumulative errors you're going to get. So it's sometimes not a variable that you're going to necessarily need, but if you want to have it, we can do position. We'll also do the cumulative trapezoidal integral. It will be with respect to time, and we will integrate this time the velocity. All right. And so we'll run that. We won't graph it because I think we get the idea there of what we've got. So now we've integrated everything, but now what we need to do is trim this, because all of the data now are from the integration start. But we really want the data to now trim from the start of the trial. So here we're going to crop the curves. And so what we'll do is FZ will be equal to, now remember, the integration start is going to happen before the CMJ start based on the way we calculated it, right? So what we're going to do is crop the FZ. So the new FZ will be the old FZ. But we're going to go CMJ start. That's the frame number of CMJ start minus int start. And we're going to go to the end. So the row that FZ now starts on will be whatever this is, so CMJ start minus int start. If I do this real quick in the command window, you'll see that's 200 data point difference. So we're actually going to change that curve by 200 data points, kind of pushing it forward. Okay, so that is that new FZ. So if I were to, you see, right now before I run that, I'll plot the old FZ. That's where the integration start happened. If I run this, I'll close this figure, or actually I won't even need to. I'll plot the new FZ, and now you'll see it starts at, maximize, the start of the jump. Okay, so we're just kind of cropping away all that stuff we don't need anymore. Okay, we'll do the same thing for acceleration. So we'll overwrite acceleration, and what we'll do is use this same line here, okay, because we're going to crop the acceleration using the same methods. We're going to do the same thing for velocity. We'll do the same thing for position. Okay. Finally, rather than cropping time, we'll just copy this time script here, this line, paste it here, and just calculate an all-new time curve based on the FZ. So nothing's changed here, we've just overwritten it because we don't need it, the old one anymore. So when I run all these, oops, I don't want to do the FZ, don't want to crop it twice, we'll have our new information. If we look here in the workspace, our saved variables, velocity is now 4904 data points, as is time, as is position, as is FZ, as is acceleration. Okay. Now if we wanted to, in our script, get a little spicy and create a figure. Now this won't be a good figure because at the end of the trial we haven't trimmed anything or found takeoff or done any of that stuff. But sometimes it's good just to create a plot of these two things together. And so I can do a plot here, and I can plot time FZ. Okay, and I'll just run through this and then do the whole, run those lines so you can see what happens all of this. So we're going to plot FZ. We're going to give it a Y label. So that is the Y-axis label. Type it. Anytime we type text, we've got to put a single quote. This will be force in units of newtons. We'll give it an X label. This will be time in units of seconds. Now what we'll also do is hold on. Well, actually, up here at plot, go ahead and make a little adjustment. Go h1 equals. We're going to give a handle name for that plot. Now we're going to say hold on because we're going to continue plotting and we don't want it to override. We're going to now do what's called YY axis right. That means we're going to move the plot to the right axis and add another one. So if you think about a common force and velocity curve together and they're on one on one axis, one on the other, that's what we're doing here. And now what I'll do is an H2 equals plot, and we'll plot time and velocity. I'll give this a Y label of velocity in meters per second. Okay. And then finally what I'll do here is give this a legend. Now in the legend, this is a MATLAB function, so here I'll open a parenthesis, and then what I'll do is open a bracket, square bracket, and put H1 space H2. So I want to give those two things, this H1 and this H2, a legend. We're going to separate that with a comma, and then give it a name. So the name for H1 in a single quote, I'll give force. I'll do a comma, and then in a single quote, I'll do velocity, and I'll end that line. So that's giving it a formal legend here. Okay, so if I run that, I just copy all that and paste it and hit enter. There's my curve. Now it's not great because obviously there's a lot of data at the end here we don't have, and obviously the velocity does a huge change here. But let's just say we wanted to present this and you say, okay, well, approximately 0.769 seconds. So what I could do is go up here and go to View, Property Editor. My property editor opened on the wrong screen. I'll move it over. So this gives me a bunch of edit properties. So you see I can edit the y-axis, all the axes. It goes till 5 seconds, but if I said, what was that, 0.79 or something like that, I can edit that. And there we go. So it wasn't quite right, but you get the point. So if you wanted to create a nice figure, whether you're writing it for a manuscript or whatever, you can do that here. Other things you can do is click on these lines. You can do this programmatically in the script. We'll get there in later videos, but you could just change, what type of line you want, the thickness of the line, the color. So if we did dashed, thicker line, give it a red. We'll use Texas Tech colors. You can do that. You can also click on this guy here, change its color so it starts to match. We can change all these axes colors. Oops, I grabbed the wrong axis. But you get the idea. You can customize this pretty much the way that you want. You can click on the legend, drag it around, right click, change its font. Those are useful. You can go up here and insert text arrows. Right, so if you wanted to do that and go min velocity, well, there you go. You have all that kind of stuff. Now we can add all this stuff in programmatically. We'll get there in a few videos down the road. But it's good to know if you just want to whip up a quick figure. I know I just whip up figures all the time and email them to people and ask their thoughts, and they probably get sick of me for doing that. But it's a useful thing to do. Or if you want to create a small little presentation, it's really good. But I'm going to close that figure. And I'll actually delete this from the script.